Okay, now I'm going to discuss about the solution of the channel capacity using Murga's method. Okay, I'm going to solve the problem on the Murga's method. Okay, so first, let me draw the problem and solve the channel capacity using Murga's method here. Are you able to see my screen? Are you able to see my screen? Okay, so first is find the capacity. Find the capacity of discrete channel. Okay, as shown in figure. Okay, we need to determine the channel capacity using Murga's method for showing the channel. Okay, so first is we have x1, that is transmitter side, and this is y1. Okay, and x2 and x3. Okay, we have y2, y3 here. This is transmitter side and this is receiver side here. Okay. This is x1 to y1. Okay, this is the conditional probability of P of y1 by x1.
Sir, your mic is off, sir.
Okay, now is it clear? We need to determine the channel capacity using Morgan's method here. First, we let us write down the conditional property. Did you copy this? Did you copy this problem? Okay, now let us write the conditional probability matrix. Okay, that is given as by using the channel matrix. So channel diagram. I'm going to write the conditional probability matrix using channel diagram here. P of Ij by Xi is equal to, this is X1, X2 and X3, and this is Y1, Y2 and Y3 here. Okay, now this is 0.8, nothing but as we see in this figure. Now let us write here only. Okay, so P of, that is P of Yj by Xi is equal to X1, X2 and X3, Y1, Y2 and Y3 here. P of Y1 by X1, how much it is? 0.8. So write down conditional probability matrix using channel diagram. Okay, next is P of Y2 by X1, this is 0.2 here. Okay, write down 0.2 here. Okay, and P of Y3 by X1, it is 0. There is no connection, so it is leave it as a 0. There is no connection, so we make it as a 0 here. Similarly, for P of Y1 by X2, P of Y1 by X2 is how much? 0.1 here. Write down 0.1. 0.1 here. Okay, next is P of Y1, P of Y2 by X1. P of Y2 by X1 is how much? Sorry, P of Y2 by X2, it is 0.8. P of Y2 by X2 is 0.8. Right, and P of Y3 by X2. P of Y3 by X2 is how much? Again, it is 0.1 here. Okay, next is P of Y1 by X3. P of Y1 by X3 is nothing but what? There is no connection between P of Y1 by X3. So make it as a 0 here. Okay, and P of Y2 by X3. P of Y2 by X3 is how much? That is 0.2. Okay, that is 0.2. Okay, next is P of Y3 by X3 is how much? It is 0.9 here. Okay, so write a 0.8. So this is my conditional probability matrix using channel diagram. Okay, so now I have to determine the channel capacity using Morgan's method. Okay, so next what I have to do? I have to write the Morgan's method concept. Okay, so let me write here again, once again, all the values. Okay, 0.2, 0, 0.1, 0.8, 0.1, 0, 0.2 and 0.8. Okay, and we need to determine, because we have a three outputs, three channels, y1, y2 and y3. So that is what we are going to take: q1, q2, q3. Okay, so we need to take the q1, q2, q3 based on the how many variables are there. Okay, so next is what we have to do. This one we have to equate with logarithmic matrix. Okay, we need to equate with the logarithmic matrix. This can be equal to 0.8. As we know the Murgas method. Murgas method is nothing but it is, let me write the generalized formula. Okay. P11 into log of P11 plus P12 log of P12 plus P13 log of P13. Next is P21 log of P21 plus P22 log of P22 plus P23 log of P23. Next is P31 log of P31 plus P32 log of P32, P33 log of P33. Okay, so now here we have to substitute the values of the probabilities using the conditional probability matrix here. Okay, so if I after substituting, it will becomes substituting the value of P11, P12, P13, it becomes 0.8 into log of 0.8 plus 0.2 log of 0.2, and this is 0, leave it as it is. And here we have 0.1 how many times? 2 times here. So that is what I will do. 2 into 0.1 into log of 0.1 here plus 0.8 into log of 0.8. Okay, and next is 0.8. Sorry, this is 0.2 log of 0.2, 0.8 log of 0.8 here. Okay, so next what we have to do, we know this matrix and we have to equate. So we get the Q1, Q2 and Q3 here. Okay, so Q1, how can we write? 0.8 into Q1, 0.8 into Q1 plus 0.2 into Q2, because we are going to multiply with this on the LHS side of your matrix. Okay, is equal to, I'm going to equate with this 0.8 log of 0.8, 0.2 log of 0.2. Now again 0.1 Q1 plus 0.8 Q2 plus 0.1 Q3 is equal to 2 into 0.1 log of 0.1 plus 0.8 log of 0.8. Again, 0.0 we have 0 into Q1, it becomes 0 here. Okay, so I'm going to multiply 0.2 into Q2 here and 0.2 into Q3. Okay, so 0.2 into Q2 plus 0.8 into Q3 is equal to 0.2 into log of 0.2 plus 0.8 to log of 0.8. Sorry.
If you are placing the satellite in a lower orbit, okay, propagation loss is different.
Okay, so now if I
Satellite, if you are going to use in the stationary, because
if I simplify,
stationary orbit,
what will be the value for this? Will you tell me? On the
minus
RF,
0.7219.
yes,
Minus 0.7219.
yes, minus 0.7219, nothing but 0.722. And next is
Minus 0.9219.
minus 0.219, nothing but 0.922. Next is same as of above, minus 0.722. Okay, so now next is what? We need to determine the value of Q1, Q2 and Q3. We need to determine the value of Q1, Q2 and Q3 here.
So these are one important parameter which need to be considered when designing the satellite layer. So propagation consideration. Along with that, noise concentration and different related problems.
Okay, what will be the value of Q1, Q2, Q3? Let me write overall expression of your this equations. Point. So let me write the simultaneous equation for all expression. 0.8 Q1 plus 0.2 Q2 okay is equal to minus 0.722 and next is 0.1 Q1 plus 0.8 Q2 plus 0.1 Q3 is equal to minus 0.922 here. Okay, and next is 0.2 Q2 plus 0.8 Q3 is equal to minus 0.722. Okay, so these are the simultaneous equation. So we need to determine the values of Q1, Q2, Q3. Will anybody simplify and tell me the answer?
And level layers or downwards. So we have K band upper and K band lower, depending on the bands using of K band down. Now this is FSS uses this particular bands. Now you go for this BSS, broadcast satellite services, which use K band and K.
Will you tell me the answer for Q1, Q2, Q3 using the simultaneous equation?
This the upwing frequency is 30 gigahertz and downwing frequency is 20 gigahertz. MSS uses mobile satellite service. Okay, these are the intended application. So where we use L band and S band, that is operating frequency. What is this L band? L, S, C, X, A, K.
Q1 minus 0.655
Frequencies.
Q1
minus
minus
0.655. 0.655.
okay,
Q2,
and Q2
60 hertz, that is C band.
Minus 0.988.
minus 0.988. Next Q3
Same, sir. First one.
hmm?
Minus 0.655.
Yeah, minus 0.655. Okay, so we got Q1, Q2, Q3 here. Next, it is channel capacity. Channel capacity is channel capacity. Channel capacity, it is given by C is equal to logarithm of 2 raised to Q1 plus 2 raised to Q2 plus 2 raised to Q3. Okay, it will equals to logarithm of 2 is to what is the Q1? Q is minus 0.655. Okay, into 2 I will do it because we have Q1 and Q3 which is same here. Okay, Q1 and Q3 which is same. Okay, into 2 I will do plus 2 into minus 0.988. Okay, what is the value for this?
0.8272.
0.8272.
72.
Unit is bits per message symbol.
Propagation conservation. The effect of atmosphere on the signal is single propagation conservation.
Okay, and next is the channel capacity in bits per second. If they ask channel capacity in bits per second. Okay, if they ask, it is given as 0.8272, that is whatever you find channel capacity, that value 0.8272 into RS. Okay, if RS it is given, let me assume RS is equal to 10,000. Okay, let me take RS is equal to 10,000. If you multiply, it will become 0.8272. If it is given, if it is not given RS, okay. If they give, if that channel capacity in bits per second means you have to multiply that channel capacity into 10,000 bits per second. How much it is? 8272
8272.
bits per second. Is it clear?
Minimized or reduced. It is because of this cloud attenuation. Cloud is present in the atmosphere, right?
Okay, this is the finding of the channel capacity using Murga's method here. Okay. Any doubt in this?
No, sir.
Atmosphere is cloud, cloud is cloud. So if it is called a cloud, what power should be? Okay, what power you are?
Okay, let us solve one more problem.
Synchronization. Troposphere is an atmospheric layer, so where we have the problem of absorption and change in the signal characteristics. And we have this rain attenuation and the depolarization. So because of rainfall, the electromagnetic wave that we are launching from transmitting and maybe reduced. That is the signal undergo
Okay.
attenuation.
So let us have one more problem.
This rain and there will be depolarization also. That is because the characteristics of water molecules, the electromagnetic waves will change its characteristics. If you are launched the signal in vertical polarization, there will be deviation in the polarization, so that it will become difficult for receiving antenna to the signal. Drawing radiation and depolarization need to be considered while designing the satellite link. We are the science civilization, that is the other place in the atmosphere. So in ionosphere, there are many presence of ions. These ions will absorb radiated power.
Okay. So now next is the problem it is given. Okay. So find the mutual information. Find the
So here when you
mutual information
not follow line of sight.
and channel capacity
This was not the directions. We undergo
as shown in figure.
the of the signal.
Okay. So what they given? First is let us write a channel diagram.
Activation of the signal. Our different layers of the atmosphere. So we have
Okay. This is x1,
mesosphere, ionosphere,
x2,
here,
y1, y2 here. This is 0.8.
That's the surface.
Okay. And this is
14 kilometer.
0.7. Okay. What will be the value for this and this? Will you tell anybody? Because this is binary symmetric channel. What will be the value for this from P of y2 by x1? If this is P, this is P, that is 0.8, and this is becomes 1 minus P, nothing but 0.2 here. And if this is P, 0.7, and this becomes 0.3, that is 1 minus P here. Okay, first write this one, conditional probability matrix. P of ij by xi is equal to, okay, this is x1, x2, and this is y1, y2. P of y1 by x1 is 0.8, and P of y2 by x1 is 0.2 here, and P of y1 by x2 is 0.3, and P of y2 by x2 is 0.7. Because it is a binary symmetric channel, because we have two inputs and two outputs. That is what we consider as A and 1 minus B here. Okay. So I need to determine h of I of x, y here. Okay. So next is what? So we have to construct the joint probability matrix. Okay, joint probability matrix can be P xi comma yj is equal to of xi of P of yj by xi. Okay, so we need to determine the conditional probability matrix here. Okay, and also here P of x1 and x2 is given in the problem. Okay, P of x1 is equal to 0.6 and P of x2 is 0.4. It is given in the problem. Okay, this is P of x1 into 0.6 and P of x2 is 0.4. It is given. So what we have to do? We have to multiply for all the elements of the conditional element, for all the elements of the conditional probability matrix with P of x1 and x2 here. It becomes joint probability matrix. Okay, 0.6 into 0.8 is how much? P of xi yj into this is 0.48 because 0.6 into 0.8 here 0.48, 0.6 into 0.2 it is 0.12 and 0.3 to 0.4 it is 0.12 here and this is 0.7 into 0.4 it is 0.28. Okay, so we determine the conditional probability matrix here. Okay, and next is what we have to determine. Actually, we need to determine I of x comma y here. That is mutual information we need to determine here. Okay, so for that again we have formula called h of y by x. Okay, h of y by x because here I of x by y is given as I of x comma y. It is given as h of y minus h of y by x. This is the formula for your mutual information. This is the formula for mutual information. Okay, so we need to determine I of x comma y is equal to h of y minus h of y by x. Okay, so you do it or else I continue in the next session. Okay, you try to solve this one. Okay. You try to solve this one or else I will continue in the next session here. Okay, so let me download the attendance.
Is estimated from alpha is equal to A into R into AR raised to B. So A and B are constants which are frequency and temperature dependent. R is location of interest. This relation due to rain is given by the equation alpha. So usually we mention or we use alpha for mentioning this alpha. Okay, for relation